Alrighty, what is going on, everyone? So we are actually now, this is the last component calculation section for our project video. So this is going to be the EMI input filter. So let's just go and check out. They don't actually have an EMI input filter featured on this schematic. Let me see if this reference design. This one has one, right? So the EMI input filter that we're going to be using or designing, sorry, is going to be like you have these X caps, this common mode choke right here, these Y caps, and then there's like some filtering caps right here as well. That those are all part of the EMI input filter, and so I'll get into a detailed explanation of kind of how we went about doing that. So just a quick summary. So the EMI filter's job is to attenuate the noise generated by a power supply. So if you want a more detailed explanation on this, I actually just published a video going in detail about EMI basics, and then I gave an example, a design guide for an EMI input filter. But the gist of it is that the input filter's job is not to protect our power supply from noise. It's to not to protect our power supply from noise coming from the wall. It's to protect the wall from noise coming from our power supply. When I say the wall, I mean like the wall outlet, as in noise will travel into the socket all the way up to the power lines, and then it'll just be like huge amounts of noise that will cause all sorts of problems. So the FCC has deemed that to be a problem, and so we got to do something about it. So with that being said, we'll just jump right into the design notes I have here. So the components that we'll be working with today are going to be the X caps, the Y caps, the CM choke, the filtering inductor, and filtering capacitor. So actually, there was not a filtering inductor featured on this circuit, but don't worry, I'll still cover everything. Okay, so common mode choke notes. Our switching frequency is 110 kilohertz, and the current waveform is a sawtooth, roughly, right? We're looking at like some type of triangular looking sawtooth type wave. I think I covered something like that in that other EMI video I did, so go check that out if you want more information on what we're dealing with here. But basically what I'm trying to do is get an idea of what type of noise we'll be dealing with. So we know that the fundamental, like I said, we'll have a fundamental at 110 kilohertz with upper harmonics going into the 1 megahertz region, right? So hopefully that makes sense to you. If it doesn't, I would say, again, go back and watch the previous videos I made. Hopefully that'll answer your questions. If it still doesn't, drop a comment down below, and I'll be happy to make more videos talking about what is the case. But just know that we're trying to deal with a switching frequency of 110 kilohertz, right? So what we're going to do is choose a choke that properly attenuates those frequencies. And the way you do that is the choke's data sheet will actually have values. Will actually show you a graph, and let me see. I don't know if I can pull it up. I actually show you how to do that in that other video, actually. So go ahead and what we're doing is we're just going to kind of shop for some chokes, look at their the amount of attenuation they offer across the frequency spectrum, and then pick one that properly attenuates for us at 110 kilohertz and beyond. Right, so we're looking in the 110 kilohertz all the way up to 1 megahertz region is what we're trying to attenuate. So that's the process for selecting a common mode choke. So hopefully that was pretty straightforward. Again, if you have questions, drop a comment and I'll elaborate on it more. But I think between this is just the example part of like showing you how I'm going about choosing mine, and then all the theory behind this also is more detailed again in those previous videos. So the next thing we want to consider is the current rating of our choke. So whenever we're selecting our choke, we have to understand how much current's flowing through it, and we want to make sure it's appropriately rated so it doesn't burn up. So on the choke, the way we're going to calculate the amount of current flowing through the choke is we're going to use this good old equation, Pn equals P out divided by this Greek letter, which I do not know. It is for efficiency, right? So P out divided by efficiency, so we're estimating an efficiency of 0.8, which means we're expecting a Pn of about 150 watts. 150 watts times the worst case. Okay, so here's I'll tell you this. So the reason we're using 85 volts AC for our V in value and not like 120 is because this choke, it goes before the rectifier. So we're not dealing with a rectified 85 volts, which would be 125 volts DC. We're dealing with 85 volts AC as our minimum input voltage, right? So that's the amount. So with that being said, that's the amount of current that we'll be dealing with for our maximum input current. So you need to make sure your common mode choke is rated above 1.76 amps. I don't think this is much of a challenge. I think many common mode chokes are rated this high, so just be careful when you're picking one. Other things to note, so the common mode chokes are actually really big components. They stand out. I think I showed some pictures of them in that other video. They're typically through-hole components because they have this giant magnetic ring. I say giant. It's one of the biggest components on a typical power supply, right? That stands out the most. Like it's like the next, like it's like second behind those bulk capacitors, right? So it's pretty big. It looks like a donut. So it's packages through holes, what I'm saying, because they need all of that strong mechanical strength that is offered by that. So that's the type of package you'll be looking for. So don't worry about it too much. There's not much you can really do about it, and it's not really that big of a deal in terms of like routing and stuff like and component placement. There's not much you can really do about this, honestly. So, which means it's fine that the choices are easy because of that reason. So. Moving on to the X capacitor notes, I'm going to say to pick something that gives us a decent power factor. So again, if you want to understand what power factor is, go back and watch. I think I did a video. It's on EMI. I did a video on it. It's the EMI video again. So I'll link that video in the description. I promise you. Don't worry about that. So we're just gonna do a quick power factor calculation. So at 60 hertz, 265 volts AC, 1.32 microfarads is the maximum value we want. So if you want to see how I did this calculation, it's going to be in that video linked below is an example of how I did it. So that means we want 1.32 microfarads is the maximum we want. So we're going to pick something like 0.33 mics to give us good margin. And these are going to be the X capacitors. So if you want to know what the X caps are, it's just one X capacitor right here. So this is the thing that's going to have a capacitance of 0.33 microfarads. And so the thing with this is X capacitor is actually a very specific type of capacitor that is in like under the umbrella of safety capacitors. So I actually showed a picture of one in that video that'll be linked in the description. It looks much different than other capacitors, like this big blue box. It's because they're rated for safety, because their failure can result in catastrophic malfunction of our power supply and potentially cause harm to an individual or an electronic device that's hooked up to it. So for that reason, these things come in a package that is usually through hole, and they are extremely large. They're up there with the size of our common mode choke, right? So these are like some of the biggest components we got to deal with on the board. So yeah, again, there's nothing nifty you can do with the package size in terms of something that will help your PCB routing or anything like that. Your hands are pretty much tied with this. So don't worry about it. Just make sure the voltage rating is appropriate and pick something with the capacitance that gives you a good power factor. So yeah. Y capacitor notes. No Y caps in this design. And the reason for that is if you look all the way back at our spec sheet and block diagram, we had specified input connector to be this, and since if you look at the circuit, the Y caps go between our line and our neutral and chassis ground, and we don't actually have a chassis ground connection because our connector only has two like prongs, only has a line and a neutral, so we don't actually have anything to connect these Y caps to, so we don't actually need a Y cap. So that solves that problem, right? You know, best way to pick a Y cap is to not do it. So yeah, that's all we got to say about that. So next thing we're going to talk about is the filtering inductor and the filtering capacitor. So this is going to be, I don't know if I have, there's no example I can find quickly for it, but it's going to be it's going to form a pi filter, right? So we're forming a low pass with a cutoff frequency around 110 kilohertz. This looks like a pi filter that's right around our smooth. This is going to go right in line with our smoothing capacitor, right? And so we want to filter at 110 kilohertz. So we want to go, we know that the cutoff frequency for an LC filter is going to be equal to 1 over pi times LC. So we need to select L to be 112 microhenries. This was arbitrary. Again, this is like, I'm using like some application notes and other guides to kind of pick these values. So yeah, so like we said, if you pick 112 microhenries to equal the inductor, then you can solve for our capacitor value. And we're picking 100 kilohertz as our cutoff frequency just to give us a little bit of headroom there so that we already started filtering a little bit before we actually need to, just for a little bit of benefit there. So then you just do the math and you figure out that C needs to equal 45 nanofarads. So what I'll say here again, of course, make sure your inductor is properly rated. Actually, talk about this. Make sure the inductor current rating is appropriate. I'm so great at this. 150 watts equals 120 volts DC times IN. So remember, we're doing 120 volts DCs because the filtering inductor is actually on the other side. So the filtering inductor is going to go right around here somewhere. And so it's already on the other side of that rectifier. So we're dealing with a rectified voltage, which means our minimum DC voltage that we'll be dealing with is 120 volts DC. And then we have IN is equal to 1.25 amps after we solve for that. So we just got to make sure that our inductor current rating is above 1.25 amps, which should not be that difficult to find something like that. And then lastly, make sure the capacitor's voltage rating is appropriate. So we have 265 volts AC turns into 375 volts DC. So this is the highest DC voltage that we should be dealing with. So just make sure your capacitor voltage rating is above 375, which is pretty, this should look pretty familiar with picking any capacitor that comes into context with the bulk voltage. So that's pretty much all the notes I have on the EMI input filter design. So this actually wraps up the entire circuit design section of this little video series. So next we're going to be starting to talk about, actually show you how I go about designing the schematic in Altium. And then we're going to be talking about the actual routing and layout guidelines. So I'm going to go through an in-depth guide for routing, and I broke it down by section, right? So we're talking about routing the AC input, then we have the primary side, and then we have all this other stuff. So I'll be going in as in-depth as I can with the layout. So please drop a like if this video helped you. It will really help out my channel a whole bunch. And please subscribe if you want to stay up to date with the rest of the videos in this series. I'll be dropping them regularly. If you have any questions, then drop a comment below. If you have any projects you want me to do, drop a comment below and I will add it to the list of projects I'm working on. Any other suggestions you have for me, just anything related to electrical engineering you want me to do, drop a comment. I'd really appreciate some feedback from you all. I'm just trying to provide as much value to you all as I can. So yeah, your comments are extremely appreciated. So that's pretty much all I have for this. So thanks for watching if you made it to the end of this video. Hopefully I will see you in the next one.